look at some additional properties of the Fourier series. Let's take a look at trigonometric Fourier series, continue our discussion. I want to take a look at some symmetry relationships. These can simplify your work in calculating Fourier series coefficients. Recall that we calculated the amplitudes of the cosine terms using this formula. I'll write it in the form of integrating from minus t0 over 2 to plus t0 over 2. And omega 0 t dt. And then for Bn, we also have 2 over t0 plus t0 over 2 x of t, sine of n omega 0 t. Okay, these integrals as written are symmetric about the origin, so integrating from minus t0 over 2 to t0 over 2. Of course, if the integrand is odd, that integral would be 0 if the integrand has odd symmetry. Cosine, of course, has even symmetry, while sine has odd symmetry. So the symmetry of the integrand of this product then depends on the symmetry of x of t. But you have the case if the product of two even functions has even symmetry, as does the product of two odd functions. So if x of t is odd, since sine is odd, the product would still be 0. You get an odd function if you multiply an odd function, say sine, by an even function, or if you multiply an even function, cosine, by an odd function. So that leads to the following properties. If x of t is odd, then you have all the an would be 0. So there's no need to actually try to formally evaluate the integral. You can also use this property, although I won't elaborate here. If x of t is odd, then this product would be even, and then you could just integrate from 0 to t0 over 2, and then the coefficient in front would be twice this, or 4 over t0. Similarly, it's worth noting that if x of t is even, then if you multiply that even function times an odd function like sine, the product will be sine, and then in that case, if x of t is an even function, all of the bn will be 0. And just one other comment before we go on to a discussion of the exponential Fourier series is Gibbs phenomena. This is the term that's applied to oscillations that appear in our Fourier series approximation. So if we terminate the Fourier series after a finite number of terms, we'll see that there are oscillations in our truncated series at discontinuities of our original function. This is true even for very large n. The error between our truncated approximation and the original function goes to 0, but these oscillations result in overshoot at the discontinuities. That's all I'll say about that. There's a little more discussion of it in the textbook and further discussion in a subsequent chapter.